Hmm? It does look like it. It does look like a mushroom cloud, huh? That's a skull radiograph. But you can't tell, right? Why can you not tell? Because there is a layer of scatter radiation fogging the image and making it look like a cloud instead of a skull, right? Mushroom cloud. So, scattered radiation, which comes from a lot of different things. We learned, having your collimated field too wide can cause scattered radiation, right? But scatter is just considered a blanket of exposure evenly distributed across the image receptor, and which takes away from recognizability, visibility, contrast, right? We want optimum contrast. We don't want super high contrast. We don't want super low contrast. We want optimum. And scatter lowers contrast, makes it lower than optimum. Okay. Scatter comes from, again, many different things. Density, a denser body part will scatter more radiation. A thicker body part will scatter more radiation than a thinner one. A larger collimated field generates more scatter. Using a grid versus not using a grid gets more scatter on the image to the image receptor. So we need to know when it's appropriate to use the grids, but scatter's the thing we're trying to block here. Okay. The addition of scatter radiation adds to exposure at the image receptor. It affects the contrast, the subject contrast, and it destroys image quality. Okay, and secondly, scatter is harmful to patient as well as X-ray techs, but we'll get to that in radiation safety. So, causes of scatter. I mentioned a few of them. Let's just kind of itemize them here. High kilovoltage. Okay, what's the kilovoltage controlling in the primary beam?
Power.
How do you mean? I think you got it right, but what do you mean?
The push. Yeah, the push, the force.
The force for
The beam.
So higher kilovoltage does what?
More power. More beam.
Yeah, I think you got onto something. It makes the beam more penetrating, right? Kilovoltage changes the power inside of the X-ray tube, right? So you can, by raising kilovoltage, you can make the X-ray beam more or less energetic, right? Making the X-ray beam more or less penetrating. Okay, so let's high kV levels. So even though less scatter is initially produced within the patient, it is emitted in a direction more toward the image receptor because it's higher energy. The scattered radiation tends to continue on towards the image receptor rather than scattering in random directions around the room. So more scatter gets to the receptor with higher kilovoltage. The X-ray beam is more penetrating, but you also deliver more scatter to the receptor. So what are some benefits? Why would we use high kVp? Okay, we need to use the right, so we don't want to use high kVp, we want to use the right kVp. Optimum, exactly. So we want to ensure adequate penetration to the body part. That's why we use high kVp sometimes. A thick body part requires high kVp. Thicker body parts are going to scatter more, so you're going to get more scatter at the image receptor with high kilovoltage and thick body parts. It's good to use high kVp along with low mass techniques to reduce patient exposure. But you're reducing patient exposure keeping in mind that you're going to make more scatter at the image receptor. So you have to account for that. Remember, most things that we do, if they're good for the image, are bad for the patient. And if they're good for the patient, they're bad for the image. Okay? In this case, high kVp, low mass, good for the patient, bad for the image. Okay? But it's a reason to use high kV. kV lengthens our grayscale, okay, lowers our contrast. So if we want lower contrast in a particular image, like a chest x-ray versus a hand x-ray, you want lower contrast in the chest x-ray, so we use higher kV, understanding that we're going to produce more scatter, okay. Number 2 on here, things that produce more or less scatter, field size, okay. Larger field sizes produce more scatter. Greater amounts of exposed tissue generate more scatter. Letting your field hit the X-ray table or other objects beyond the anatomy of interest will create more scatter. taking away visibility. As long as you're collimating big enough to include the anatomy of interest, you're doing the job you need to do. Any extra widening of the collimated field beyond that is only destructive to the image. It only adds exposure to the patient and adds scatter to the image receptor, scatter and exposure at the receptor. There is, in other words, no benefit to making your field size larger than the anatomy of interest. Okay, I should also remind parenthetically that when you turn the collimator light on and you see the light field on the table, has anyone here never seen the collimator light turned on? No? Okay, good. Everyone's seen it. It projects a light down on the table, right? What is that light supposed to represent? The field size, right? Your radiation field. It's not exactly though. Okay, there is a misalignment between where the light lands and where the actual radiation field will be. That misalignment can be as much as 2% of this SID. Okay, so let me give you a number here, right? So you've got your field size, right? And then you've got your actual radiation field that might be misaligned, okay? And you might want to know how much is that misalignment so that I can account for it, okay? So it can be no greater than 2% of the SID, okay? That's a rule, that's a regulation that we have to follow. So somebody will come in from the state of California, because we're in California, and they're going to check this, okay? And if you fall outside of the specification, you have to have your equipment serviced and adjusted, okay? If you fall within the specification, you're golden, all right? So let me give you what this will come out to. What's the typical SID? So we have 40 inches and we have 72 inches, right? Those are the two typical SIDs. So 40 times 0.02. I know it, but let me just do it on the phone real quick. Make sure I don't screw something up. 40 times 0.02. Sorry. 0.8 inches. Okay. So you can have at a 40-inch SID, this can be misaligned as much as 0.8 inches, roughly 3/4 of an inch. Okay. Which means when you collimate, if your light field touches the soft tissue, then you can have as much as 3/4 of an inch. Your radiation field can be this way as much as 3/4 of an inch and cut off as much as 3/4 of an inch of soft tissue, and you'll still look like your light field's aligned. Okay, give yourself about an inch of light around the body parts to account for this misalignment of the X-ray field to the light field projected by the collimator. Okay, look how big this can be at 72 inches. Let's take 72 times 0.02. Okay, it's bigger, right? But so 72 times 0.02, 1.44 inches. That's almost an inch and a half. Okay, your light field can be as much as an inch and a half off of where your actual radiation field will be. This is why it's important to give yourself light around the anatomy of interest, never larger than the cassette, and always give yourself about an inch. Okay, so when we say collimate to the anatomy of interest, we don't mean put the light up against the edge of the anatomy of interest, we mean give yourself about an inch around the anatomy. Okay, that's what over-collimating was, the first thing, one of the first notes in the first set of slides we went over. That's why we worry about over-collimating, because your light field that you turn on with the collimator is sort of lying to you, okay? And they misalign, and that's okay. You can test this misalignment. We'll do it in one of our laboratories that we'll get to. We do it. We make a light field that's 10 by 10 inches on a receptor, and we place metal objects all around the edge of that light field, and then we make an exposure and we see if those metal objects fall inside of the actual exposed area. Okay, they're all on the outside of the area, and we see how far inside they fall, and you can measure it and get a number from it. I've watched state inspectors come through, and they quite literally take paper clips and put them around the edge of the light field, make an exposure, then measure how far inside of the light field some paper clips fall, and they'll get a number from it. You have to be less than 0.8 of an inch at 40 inches, and less than 1.44 inches at 72 inches of SID. And if your SID were bigger or smaller, that number would change. They only test at one SID, they test at 40. Okay, so if you're aligned at 40, then you're aligned at 72.
Do you think eventually they'll get it like precise?
How do you mean? Oh, like get the
Yeah.
equipment to line up perfectly? Definitely. And it's adjusted, and it falls out of adjustment periodically. The light inside the collimator, there's a light bulb inside of the collimator, and it has a little reflector, and that reflector has to be adjusted, and you can dial it in pretty close. You just can't. So some offices might be completely dialed in, right? Most of the time there is some misalignment. So like here, there's like a 0.5 inch, almost a ½ inch misalignment, which is obviously within the spec, but yeah, everyone's going to have a little bit, yeah, and it can be more or less dialed in. It just can never be more than those numbers, yeah. Or else, what's the point of even having a even having a collimator light if it does not showing you where your radiation field is? Yeah, and that's why it's so important to have your collimator light working. Okay, one thing I'll do when I go into inspect offices to make sure they can train students is well, this one doesn't have it. I'll press the button on the collimator and I'll make sure it turns on. Okay, because if your collimator light doesn't turn on, how in the world are you going to line up the body part to the cassette and anything like that? I have had that happen where it went out in the office. It's like, we need to keep taking X-rays, and you're guessing, and you definitely should not be doing that. Right? It's just not a good way to do it. So I would advise you to make sure that your office has backup light bulbs for their collimator, unless they've got a service guy that can get out there that day, or they're just okay with having their X-ray room go down until a service person can get out. It's really important to have backup light bulbs. It's just a light bulb. There's usually a little bracket right on the back. Take it off, replace the light bulb. It could not be easier. So you want to know which light bulbs they are and how to find them, and they're not cheap. They are kind of expensive. They are usually light bulbs that are used in projectors. So projector light bulbs can be kind of expensive. Anyways, that's something to think about. And I bet you they're going to get nicer and nicer as more and more equipment comes out, and better alignment, things like that, as nicer equipment comes out. But the limit will still be there. That's the biggest limit. Okay, the third thing that affects scatter radiation is the thickness of the part. Thicker parts mean more tissue, right? So you think like your collimated field is a size, right? But the part has a thickness in this dimension, independent of the size of your collimated field, right? You can have an 8 by 10 collimated field and a part that's 1 centimeter thick, and another part that uses the same collimated field but is like 12 centimeters thick, right? Thickness matters, and that adds to the volume of tissue that is irradiated. Remember, just pick let's go back to an image, right? Any image, I don't know, this one, okay? Ignore the words and just look at the image. In fact, let's just zoom in on it. That's a body part, a knee, right? And if you look at just any square centimeter, like that square centimeter, right? What you see is two-dimensional. It's that way and that way, right? But what it represents is three-dimensional. Yeah, that part has a thickness to it, okay? This has a thickness, that has a thickness, every part of the body has an associated depth or thickness to it. That's not shown on the radiograph. You can't see that dimension, right? But the X-rays had to get through that dimension to get to the image receptor. Thickness matters, and as a part gets thicker, it will scatter more X-rays because the X-ray beam is interacting with more tissue because of that increase in thickness.
So the gray haze on the outside of the bone is very clear.
The what on that?
Just to the outside of the bone, the border of the bone.
Like that?
Yeah. So
okay.
Where your hand is,
yep.
That's
cortex.
Obviously, it's tissue.
Yes.
But then, do we also consider that scattered, that haze? There's a haze across there.
This,
or is it? You know? So you understand what I'm saying?
Yeah. So this haze is from grid lines.
Okay.
So this is not a good image.
No.
Not a good representation, but I was using it just because it was the closest image in the slide. But Are you talking about this stuff?
Yeah.
So
Yeah.
this is just, for the one, this shows model. Remember model? Graininess,
Yeah,
right? This is underexposed, okay? It's underexposed because there was a grid put in the way, and they didn't change their MAS or KV to account for the grid, okay? So it's modeled. That's the problem here. That's why it's got this sort of hazy, grainy appearance to it. All to do with technique, MA or KV.
But relatively unusable information on that side of the boat. I mean, we can still see a few things from the
Yeah,
boat.
I mean, there's
It's not a great
there's
picture,
definitely
but-
less information. Yeah.
Yeah, it's less information of the, like, perhaps there was a sarcoma in there. We couldn't.
Yeah,
We
right.
might not be able to.
It's not gonna show up because the information's not there.
Right.
Yeah, absolutely.
You know, use my big word.
So part thickness has an effect on scatter. The thicker the part, the more it scatters. So the point is, we want to reduce scatter, and we use a grid to do that. Okay. Thinking about a body part, that knee that we just brought up on screen, you can't make that part thinner, right? That part has a KV that you'll use for it. You're not going to use a different KV than you would use. That the KV you use is the KV you use, right? What are the three things that affect scatter radiation? KV, field size, and part thickness. The part is as thick as it's going to be and you can't change it. The KV is whatever it's going to be and you're not going to change it, okay? And the field size is what it's going to be and you can't change it. Those three things that affect scatter, you cannot change for one given exam. So the only way to reduce scatter for some given image is to just stop it, okay? Stop the scatter, okay? So grids came about in the early 1900s. You have 1913, somebody named Gustav Bucky. And so now you know where the name Bucky tray comes from, okay? It's somebody's name, yeah? Gustav Bucky developed something called a grid, okay? Another person named Hollis Potter modified the grids later on in time, so we sometimes call them Hollis Bucky diaphragms, okay? But most of the time we just call them Buckies, because he was the first one. Usually the first person gets to hang on to the label. Anyways, the point is, if you look at this from the top to bottom, you have a focal spot emitting radiation. Those lines coming down represent the primary beam spreading. You have a object, a body part that scatters radiation. Body part, X-ray beam interacts, and there are tissues in the body that will scatter. So we're seeing all the scattered X-rays going in all sorts of directions. Scatter goes everywhere, in all directions, okay? With higher KV, more of it goes this way, but it goes everywhere, okay? The grid is placed in between the patient and the image receptor, and the grid's job is to let the information carrying remnant beam through and to stop the off-focus scatter radiation going that way, and any of these random weird directions. The lead strips will just catch the scatter, will absorb it, attenuate it. Okay. So that's the idea with a grid, and we just need to now learn about the different types and how we categorize these grids. Okay, so yeah, here's the more up-close idea, right? X-rays that do not travel parallel to the grid, such as the ones that I'm drawing the laser pointer along here, X-rays that travel at an off-focus angle will not make it through the grid. Okay, they just will be captured by the grid. Remember, X-rays can't round a corner, right? They can't see the grid and go around it. They travel in straight lines, and so they're going to travel in whatever direction they're going, and they will be absorbed by the lead strips. The lead strips have to be upright or angled, and there has to be space between the lead strips. If it's just a blanket of lead, then everything gets caught, right? So you have to have a gap between the lead strips for the useful stuff to get through and the unuseful stuff to run into the lead strips. So then there is now a relationship between the height of these strips and the space they are apart, and how many strips there will be per millimeter. There's a number of quality factors that we put onto these grids, so we'll get to that in just a quick second. Minor note, some grids are stationary, If you've been in my x-ray room, you've seen the stationary grid, the big white thing that slides over the cassette. Okay, stationary grid. If you've ever used a table bucky or a wall bucky, you've used an oscillating or reciprocating grid. Both mean the same thing roughly, the grid moves. Okay, things that move during an x-ray exposure get blurred out. Okay, if you don't want to see the grid, you make it move during the exposure. Okay, you shake it around. Reciprocating or oscillating grids do that. Reciprocating grids just move back and forth. Oscillating grids kind of move like that. Okay, it doesn't matter really, but they move. Two major things for efficiency or effectiveness of our grids. It's going to be two things, either grid ratio or grid frequency. There are other talks like lead content and stuff, but the two main things that control how effective a grid is at catching scatter are those two, ratio and frequency. So let's look first at ratio. Ratio is just the ratio of the height to the width between the strips. So not the width of the strips are very thin, but the width between the strips. How much space there is. If there's a lot of space between the strips, then more x-rays can get through at steeper angles, right? If there's less space, less x-rays get through and they have to be traveling more or less parallel to the space, okay? As well, if the grid is very tall, the angle that an x-ray could come through at has to be shallower, and if a grid is very short, the angle can be steeper, okay? So the ratio of the height to the width of the interspaces is very important. And it's independent of the actual measurement, right? I mean, it's affected by the actual height and actual width, but it's just a ratio, you know. As we said before, an 8-to-1 grid can be 8 millimeters high and 1 millimeter wide, or it can be 4 millimeters high and a half millimeter wide, or 2 millimeters high and a quarter millimeter wide, right? All of those would be an 8-to-1 ratio. It's just saying an 8-to-1 grid has strips that are 8 times taller than the space between them. A 12-to-1 grid has strips that are 12 times taller than the space between them. Okay. The height of the strips determines the overall thickness of the grid plate, and the width doesn't affect much except for frequency, which we're going to talk about on this next slide. So you can think about looking down on the grid from the point of view of the X-ray tube, and you see just a bunch of lines, just a bunch of lines running the length of the grid, right? And what you can count is you can count how many lines there are per some given amount of space, millimeter or centimeter or whatever, okay? So that's frequency. The number of lead strips per centimeter, because we said so, when scanning transversely across the grid. That just means imagine looking at the grid from up top on it like that and counting how many strips there are per centimeter. 24 to 80 lines per centimeter, commonly between 32 and 43. Do I remember that? No. Okay, that is one of those things that I'm just going to read right from here and go, that's what it is, and you should practice remembering it. Hang on to it when you take all your tests and stuff, and then after you're done testing, you're out there as a practicing x-ray tech, grid ratio is the only thing that matters, okay? Because that's what actually affects the effectiveness of the grid is the ratio, and all I need to know is a 12-to-1 grid is going to absorb more scatter than an 8-to-1 grid. So I need to know which one should I use, right? And here's the other tip and trick, you're probably only going to have one. Right, you will have a 8-to-1 grid or a 12-to-1 grid. You're not going to have a suite of them to choose from. Okay, your buckies are fixed. Your buckies just are what they are, and whatever their ratio is what they are. They don't change. Okay, but you know you're at one office and they have an 8-to-1 grid. You go to the next office and they have a 12-to-1 grid, and you're going to need to know that those are different. So there's a lot of, in theory, this is what happens, but then in practice things may be a little different. So couple examples here with frequency. Okay, So these two show grids that are 10 millimeters tall. Both of these are 10 millimeters tall, but 4 millimeter spacing between the top on A, and 3 millimeter spacing between the one on B. B is going to have a bigger ratio, right? The width of the strips is relatively narrower compared to the height. So the ratio is going to be higher for B, but that's not the point here. The point is there's a number of these per millimeter, 1.6 lines per millimeter versus 1.3 lines per millimeter. This one has a higher, the F number, frequency is higher, okay? Grid ratio is 2.5 to 1. This one's 3.3 to 1. The one that has a higher frequency also has a higher ratio given a fixed height. These both would have to be the same height, okay? So for a given height, more lines per centimeter, or lines per millimeter, doesn't really matter, more lines per millimeter is going to be a higher ratio for a given height. Now check these two out. These two grids have different heights and different interspace widths. This is 10 millimeters tall, 4 millimeters wide. This one's 7.5 millimeters tall, 3 millimeters wide. But look at the numbers here. The lines per millimeter are different, frequency is different, but because the heights are different too, we get ratios that are identical. This is a 2.5 to 1 ratio. 10 divided by 4 is 2.5. The grid is 2.5 times taller than it is wide. This one's 7.5 tall, 3 millimeters wide. That's also a 2.5 to 1 ratio. By the way, I'm just trusting their math here. Assume they're right, right? I didn't double check this, but assume they're right. Seems pretty simple math to me. Yeah, 7.5 divided by 3, 10 divided by 4 should both come out to 2.5. These grids are equally as effective. Okay, they will attenuate a similar amount of X-rays. Said in another way, the grid ratio is equal for both sides. The effective angle of penetration will be the same for both sides. In this case, they say 25 degrees. Okay, that's the maximum angle compared to the central ray that a beam could come through at and still pass through. 25-degree angle. 26-degree angle, it's going to get caught. Anything less than 25, it's going to make it through the grid. Anyone have any questions there? Good time to ask questions, as I'm sort of rounding this out. No? Okay. All right. Let's talk about when we use the grids. When is it a good time to use grids? So indications for use. Let's see. So your considerations, when do you use a grid and what grids to use, will vary by these three different things. The thickness of the part, the field size you plan to use, and the KVP that you will plan to use. Okay? And for me, my main consideration when using a grid or not is part thickness. That's why it's listed as number 1 here. Okay? So here's some advice, and this number, just by the way, people write these textbooks, and people are all different, okay? There's authors of each textbook that you'll read from, and those authors might come up with slightly different numbers based on the data that they base everything off of, okay? It doesn't mean they're wrong, and it doesn't mean that the next author's wrong, it just means that they're different. All right, so just keep that in mind. When I say when should you use a grid based on thickness, I usually say 10 or 12 centimeters. Okay, that's because books will say 10 or 12 centimeters. However, if you're reading from this specific text, which you are, they're recommending a grid should be used anytime a part is thicker than 13 centimeters. Okay, because parts that are that thick tend to cause excessive scattered radiation. My recommendation is anytime a body part's thicker than 10 centimeters, you should in your head be going, should I use a grid? And then decide to or not, okay? By the way, it's not all good. Grids do have a downside. I haven't necessarily gotten to their downside yet, but they have a major, major downside, okay? So that's something to keep in mind. I will get there. That'll probably be the last thing I do for today in just a second. So more than 13 centimeters, definitely use a grid. More than 10 centimeters, your ears should be perking up. You say, maybe I should use a grid, okay? By the way, roughly speaking, humerus and up gets grids used, and like knees and up gets grids used. Okay, so hands, wrists, forearms, elbows, usually tabletop, feet, ankles, tib fib, lower leg, usually tabletop, but anything above those body parts usually are thick enough to require a grid. If you don't know how thick a body part is, how can you figure it out?
Measure.
But with what?
Use a caliper.
Caliper, right? So measure it with a caliper. As you guys are practicing and you're first getting out there, make sure your x-ray techs show you where the calipers are. Make sure that you have used them, okay? I know x-ray techs get in this habit of just eyeballing things and just figuring it out because they go, I just know what it is. You don't until you develop the skill for it, right? So use calipers until you're ready to, do this. And they really, honestly, should be using calipers all the time. We just tend to not. Anyways, recommendations for ratio based on thickness. 10 centimeter thick body parts, an 8-to-1 grid is useful. Thicker body parts are going to scatter more, so higher grid ratios to absorb more scatter. 10-to-1 grids for things that are around 18 centimeters. 12-to-1 grids for things that are around 22 centimeters. Yes?
Okay, so we have a grid in the table, we have a grid in the wall bucket, right? So we can't really change, we have what we have.
Yes.
So how do these numbers, what do we do with these numbers?
Oh, yeah, so I mean,
we just adjusting our KVP and our mass?
yeah, so you're going to adjust mass typically.
Okay.
And you're right, your grids are fixed. You can't go and change out to a higher ratio grid when you've got a denser body part. I will say that in some cases, in larger facilities, they might have multiple grids to choose from, and that is the circumstance in which you would go ahead and use the thought process here and choose a different grid. But yeah, if you're using the Bucky trays, they're fixed. Usually they're like a 12-to-1 grid, and they're just fixed. Okay. Most stationary grids that can be moved around the X-ray rooms are usually an 8-to-1 because it's kind of a general purpose type of grid ratio. But yeah, usually they're fixed. So my advice is, really your actual thought process is, should I put the cassette on the tabletop and shoot this tabletop, or should I use the Bucky tray? And my advice is, anytime a part is thicker than 10 or 12 centimeters, you should probably be using the Bucky tray, okay? So here's the downside for it, okay? This is the simplest version of the downside that I'll give you. So here you go. When you use a grid, what's it doing? Like, what does the grid do?
It's blocking the exposure.
From getting to the image receptor, right?
Yeah.
So it lowers image receptor exposure. And it doesn't lower it by a little bit, it lowers it by a lot, okay? So to compensate for that, you actually have to raise the patient's exposure significantly, okay? Because the grid is not above the patient, the grid's below the patient, right? The image receptor is getting less exposure when you use a grid, so the image will be underexposed if you don't compensate your mass to account for this, okay? Because the grid absorbs radiation, some of it is useful information, so we want to go ahead and raise our MAS to account for that. So here's the recommendations. If you're not using a grid, just whatever your mass is, that's what your mass is. Let's say 5 mass for a hand, okay? If you're using a 6-to-1 ratioed grid, 5 mass for a hand would turn into 15 mass for that same hand, okay, with the use of a grid, okay? So if you don't have to use a grid, don't use a grid. Like, a hand is not that thick, 3 to 5 centimeters, right? It's less than 10 or 12. I don't need to use a grid. If I did use a grid, I'd have to give the patient 3 times the amount of exposure that they normally would get. Don't need to use the grid. I don't need to raise the patient's exposure by a lot, so I don't, right? I'm thinking in my head, Alara, keep the exposure as low as reasonably achievable, okay? And notice as the grid ratios go up, the mass conversion goes up, 5 mass for a hand. If you used a 12-to-1 grid for whatever reason, because you decided to, you'd go to 20 mass, okay? And so this is a mass conversion factor. These are just basic recommendations. Buckies are usually 12-to-1, so Buckies are a 4 times conversion. So and when you have to think about this is like body parts that kind of on the in-between, like a knee, right? A knee can be 10 centimeters thick, so in your head you're going, well, should I put them in the grid or should I not, right? If a knee would take 8 mass on the tabletop, In the Bucky tray, it's going to be what, 32 mass, right? And how much more exposure is that for the patient?
It's a considerable amount.
4 times more, right? It says to go up by 4 times, yeah? And mass is directly associated with patient exposure, so 4 times more for the patient's exposure. So if you don't need to use the grid because the part won't generate sufficient scatter, then don't use it, okay? Use the grids when you need to. How much, if you raise mass by 4 times, let's say you're using this 12-to-1 grid at the bottom, how much will exposure go up at the image receptor from not using a grid and not changing mass? Not at all. Receptor exposure will be unchanged from a no grid image. If I shot a hand at 5 mass without a grid and made my image, and then I used the grid and went up to 20 mass, the receptor is going to get the same amount of exposure at 20 mass, okay? Because the grid is catching all those extra X-rays. Who gets the extra exposure is the patient, okay? The image receptor would get the same amount of exposure, 12-to-1 grid at 20 mass, as the image receptor would get no grid at 5 mass, okay? The receptor sees this thing the same, the patient gets the extra exposure given to them. Okay, so keep that in mind. Use grids when we need to use them, not when we don't need to use them. I've got more, but not that much. What I'm going to do, I'm going to carry this over into next talk. I want to let you guys out of here without taking, if I talk, I'm going to have to talk for another hour.